and to introduce our speaker, Longbin Huang. I'll just say a few words about Longbin in a moment, but before I do that, I would also like to acknowledge the traditional owners on the lands on which we speak across the country today. For me here in Brisbane, that's the Jagera and Turrbal people, and I extend that acknowledgement of country across all the lands on which we meet. I would just like to introduce our speaker today. We're very fortunate to have Longbin presenting today. He is a full professor and a program leader at the University of Queensland, and he's a group leader for ecological engineering in mining, with a focus on ecological engineering at the Sustainable Minerals Institute. So over to you, Longbin. I'm looking forward to the webinar.
Yep. Thanks very much for your introduction, and thanks for CRC coordinating this presentation. Also, I do like to thank everyone taking the interest to listen to me. This talk is really to building, sort of try to share my experience over the last 15 years, the journey and the learning about how do you translate fundamental knowledge or science into innovative technology, which can really help the industry to solve large problems. So I will start my talk as we normally do, acknowledge the traditional owners of the country. Very briefly introduce myself about my own track in my research in the past. I'm a multidisciplinary researchers, especially doing a lot of this applied research, try to solve problems for society and for the industry. But if you look at the whole map, which I extracted from the eSpace of the university library about my past track record, there are certainly extensive needs of the research discipline, but there are also underpinning focus of discipline strengths. So if anyone wants to develop career in the industry partner research and translational research area, that's balance you may need to pay attention. And I do have extensive collaboration network across Asia Pacific and United States. And in the moment, I have a very quick introduction, my own research team of multidisciplinary, covering many discipline fields. The reason I need that is I need to synthesize, integrate them into a robust technological system to solve the problem for the industry. Now we come on to the real topic of today's talk. We start, why bother? Why do we do research? Research is really here to generate new knowledge and develop new technologies, okay? And if you look at this schematically, traditionally academia will do research purely because curiosity or strategic importance down the track, like in the past, in the beginning of Newton, observing the apple falling and start to ask the question why apple doesn't fly upwards, that lead to discovery of the gravity theory. Of course, how to utilize that theory, that's an undefined time frame. We find its own way to do the technology transfer. But more and more this day and age is problem-driven research. Society, community, and the environment have urgent needs, which has to be resolved gradually, partially, or significantly within very defined time frame. Normally, you're looking at 3 to 10 years to have gradual or significant solution. So many of the research is driven by problems, and discover the knowledge, proof of concept, and you need to partner with major industry sector to scale up those core mechanisms. Therefore, you have a technology specific to industry sectors and problems that come back to serve the industry. I mean, we have climate change, ecosystem rehabilitation, etc. And as researchers, we're always struggling between publication and technology. I just thought bring this up, especially for young, early and mid-career researchers, Sometimes we go to literature looking for answers, but we have to be very careful. Publication is really a piece of written material about short episodes of events. It may not be correct because if we're snapshots of short changes, which doesn't represent the entire process of change. But we have to do that because we have to make sure our research quality is recognized and acceptable by scientific communities. Of course, we like to share our experience and knowledge so we can advance others in the research field. Technology is very unforgiving. It has only two answers. It works or doesn't work. So technology is an integrated system housing robust mechanisms or processes described in the proof of concept. So this proof of concept, to make it into technology, has to be very tolerant of dynamics of biophysical and socioeconomic condition in the targeted operational environment. And the system, the technology has to be able to deliver the minimum amount of meaningful effects that worth the money for the users to use it. So you need to put that in the context. So what is translational research? It is saying it is a very expensive process. It is scale up core mechanisms and or processes at lab scale, then into an operational scale. But a technology, to be qualified as a technology, has to be consistently capable of delivering the least amount of meaningful functions outcome under operational conditions. So we have to get all these keywords in your mind. The operationally useful technology must have other collateral understanding. What is your biophysical requirements and conditions? Okay, materials, structural requirements, and what is your operational requirements? Who can use it, etc. So translational research is not an easy task. It does require multidisciplinary, it's the teamwork, and require investment. So let's look at the details and complexity of translational research. If you look at the whole research journey, academics are very good at in the front end. So, that's what we do. We're curious, we dream up a lot of ideas, and we try to create condition fit those ideas to make it work so we can publish exciting papers. So who can do this? The actors are scientists, very well trained, PhDs, postdocs, and researchers. But when we want to make it the proof of concept, then we need to think about engineers and technologists. But if we want to make the whole proof of concept to be workable under um, operational conditions and by the end users, the actor change, extension personnel, farmers or land users, engineers, etc. So if you look at the whole journey, how much control can you have? The operators control from highly educated, specialized researchers to workforce of low socioeconomic educational background, especially in the mine land rehabilitation area. Doesn't matter how precise we do as the researchers. End of the day, the land managers, the operators, the field, the machine operators, the excavator operators have to use your technology. So the whole journey will start to have highly controlled condition to highly variable conditions. So we have to bear this in mind if we want to develop technology useful. And if you look at it schematically, the peripheral interface to your technological mechanism has to take into consideration what is your socioeconomic interfaces. What is your operation interfaces? Is it in the sewage plant, highly engineered flotation process, or under the field condition, which is diurnal and seasonal weather conditions? So this you need to, if you're interested in translating your proof of concept into technology, you have to map out the key interfacing domain of the technological system, and you need to parameterize them because they'll become your core research questions to bring back, try to understand the influences, all these interfacing variables on the robustness. Okay. Now, that's an overview introduction of the development from knowledge into technology. Um, let's explain some of the key steps in doing so. Certainly, always first start with you need to know how robust is your proof of concept. And one of the learning I gained from what I have done is the proof of concept has to have a very solid footing in the fundamentals. So do not toss out your old textbooks. You do need to go back to classic theory, try to get real understanding. For example, I worked a lot on tailings, and especially how can we treat tailings as a parent material, therefore apply the theory of pathogenesis in nature. And by doing that, one of the key proof of concept is, can we use tolerant microbes to start weathering the minerals? That's very important part of the early events of soil formation. Okay. And so what we did is when I first start working on the tailings, I try to understand what the hell is tailings. I used to work in forestry and cropping soil. So we went through all this schematic analysis comparing primary and secondary minerals. So we got fair bit idea. Okay, base metal is dominantly sulfidic, metal bearing minerals, and then bauxite residue, aluminum silicate, secondary minerals, iron oxide, coal, carbonate, bicarbonate, quartz, etc., etc. So we started with fundamentals. Another thing we consider is we can't ask the industry to give us money forever. What can we do? What is the reasonable time frame for us to focus on? Therefore, we can design suitable engineering inputs to interfere, to regulate, and to speed up those fundamental process or the which described in the proof concept. If you look at the whole ecosystem development, soil and land, that's sort of time frame we should aim. Uh, we can't change much of geology. We can't wait for a million years to all the tailings become another natural rock. So that's what time frame, because I want to get money from industry partners so I can scale it up. Otherwise, doesn't matter how clever my idea is, it's not going to make to the daylight. And the same, we come back to the fundamental theory of pathogenesis. You look at the soil formation process and key factors. What can I do? What can I cost effectively, feasibly manipulate and interfere and regulate and speed up in the field? So we went back to 1941, the first pathogenesis theory by Jinning. And we took the key component parent material. We can't do much about it, but we need to understand it. Organism, microbes, we can do something. Okay. And what can we add, which is cost effective? Okay. So this is if someone interested in the soil formation theory, I'm sure you are familiar with this soil formation model. The second thing is I try to uh, explain the robustness. So I use my own example to show. So we apply the tolerant microbes theory to weather pyritic material and sulfides, etc. So this is when we first discover the tailings actually harbor a lot of this, and then we design the nutrient solution, try to enhance, irrigate it. Can be achieved within a couple of months. But if you don't have the weathering, the tailings stay as it is. So we sort of try to confirm the concept of proof in weathering the minerals in the sulfidic lead and zinc tailings. And the field study also demonstrate our thoughts is correct. So in highly weathered long-term old tailings, after amendment and soil formation interference, we can establish native plant species. This is the Mount Isa mine tailings. But of course, whether this approach is most appropriate for that circumstances, we certainly consider the non-polluting criteria. So we did not continue that direction. What we have done a lot by adapting this conceptual model or the proof of concept is to iron ore tailings. So the iron ore tailings is very fine, a lot of silica, a lot of biotite. So we say, can we enhance alkaline tolerant microbes to decompose the organic matter and start to weather biotite and generate aggregates? This is very critical soil formation indicator. So in the process, we discover, yes, we can. The microbes generate organic acid, start to weather biotite, releasing a lot of soluble iron, soluble potassium, the key minerals. This is work done by graduate PhD student Lachlan. And a postdoc followed up, tried to demonstrate the whole model of mineral weathering, aggregation, early plant colonization. And we actually provide the industry the whole schematic soil formation diagram and how do you enhance magnetite iron ore tailings or iron ore tailings to develop into soil. So our initial intent to establish the proof of concept of enhancing using engineering input, enhancing extreme or tolerant microbes to weather the minerals, therefore stimulate the early formation of soil events, which is prerequisite to the development of a lot of important soil property. It worked. So that has a diversity. Now, it's okay, we demonstrate in the glasshouse, in small plot trial in the field. Does it work in the field? If it doesn't work in the field, you're not going to have technology because if it becomes too patchy, unreliable, industry is never going to use it. So if we look at this, how do we do it? How do we make it into technology? Of course, we need to scale it up. Because we need to deal with not just 50 mil or 500 mil or 5 liters. We need to deal with hundreds of hectares. So we have to scale up the effects. But doing that scaling up, we're also scaling up noise. So we have to make sure whether the response to noise ratio still stays strong. Because in the controlled condition, we all know we can increase the number of replicates. We can make statistical significance to many decimal points, and then we publish nice papers. Does it matter under the field condition? Probably doesn't matter. We don't have any much control, so we have to make sure. And one of the lessons really taught me is what worked in the glasshouses may not work in the field. So you have to get the understanding. I always use this failed field experiment. This is really gave me a very good lesson. Is we initially asked a PhD student did a glasshouse experiment by using organic amendments in the sulfuric lead and zinc tailings to grow native plants, because the theories say organic matter, increasing available organic carbon can suppress the activity of sulfide oxidizers. Well, it worked in the glasshouse because why? Because the glasshouse temperature, diurnal change temperature is much small, and the humidity and moisture in the pot do not change that widely. So you have maintained relatively stable redox condition. So all right, we took the concept to the field. We set up the lysimeter 1 cubic meter each. Within 3 months, the 3 batches of plants die because the diurnal temperature, evaporative water loss, the redox change sent the oxidation of sulfide to very high rate. So we have a pH dropped down to pH 2, nickel concentration, zinc concentration, copper concentration, whatever it goes up. But as a comparison, we have a 30-year-old tailings which is very well weathered. Actually, the theory works. The native plant survived for more than a couple of years until we dismantle the trial. So this is very good example I always use is don't blindly believing your glasshouse study. Now, that's good, but that's an interim scaling up. Now, when you go to the field, you may not going to have the same type of organic matter, and you need to scale it up, and you're not going to mix your pot trial in a big barrel for 15 times, whatever. You're not going to grind so all these material condition, are they going to interfere your proof of concept, your mechanism? And second thing is, if you're going to scale it up into broad acre scale, and who's going to do it? It's not using shovel anymore. It's the diggers, it's the excavators. It's how tolerant is your technology, technological mechanism of this operational inconsistency. And so in that understanding the interference, then you can start to think about, okay, what can I do? Okay. For example, yes, I can provide some water. I can use a little bit irrigation, but I can't control the temperature. So I have to harness the seasonal. So I have to schedule. If the future, if the user is going to use that, then your field work schedule has to time with the warm season. Irrigation is fine, but you cannot irrigate forever. So you need to think about uh, what kind of irrigation water can achieve the minimum significant or useful effects. Okay. So that you need to map out and parameterize. So when you're scaling up the your proof of concept, it's not just scaling up one dimensional. We are very good at scaling up one dimensional by just treating the substrate. But how about you need to utilize the technosoil engineer from tailings to rebuild the soil plant system? That's two dimensional. How are you going to do that? And sometimes we need to integrate all this soil plant system and landform to build the landform and landscape. So you get to 3D. How are you going to integrate that? You have to bring in surface drainage. You have to bring in hydraulic processes. So there's a lot of heterogeneity and integration of different ecosystem processes, which will impact on the proof of concept effectiveness. So normally I carry out this kind of mapping. Is each level of design will impact on the upper level, and the upper level of design could come back influence the lower level. So this is just the example. So for example, in my cases, I always start from, can the macros work in that kind of condition I provided? If that works, can that lead to aggregation and change in physical chemical conditions? If that changes, how that supports sustainable plant community development? So if the soil system works, how do I put them together to build the diverse landform? So that's sort of sequence analysis and questioning you have to do by yourself. So if we take all these things together, you can see knowledge to innovation. That the first step of proof of concept is relatively easier from the operational context to from the complexity and heterogeneity perspective. But from the proof of concept to feasible technology in the real world, that's a lot of journey there. So there's a lot of effects and noise and environmental variability. If anyone interested in this, you really need to take your time to do system analysis to map out the interfacing, especially the end user interfacing is very important. Now, this is come back, doesn't matter how much you want to do. If you want to translate those concepts into technology, you need money. There's no doubt about it. Okay, without money, no business. So you really need to think about the importance of industry partnership. That's really depends on whether your proof of concept is aligned strategically with the industry's high priority needs to solve large, costly, and risky problems. Uh, Industry will not invest on significant amount. If you just tell them if you invest $1, you might get 5 cents profit. They will aim, if your technology can gain 1,000, 1,000,000 times the return, I'm sure the industry will be interested in it. I just look at my own journey, started from back in 2008 up to now. You can see each phase of the industry investment is increasing, and that consistency of investment, attracting investment, you have to be able to deliver. So one of the very proud case we have achieved is the bauxite residue technology. I think I don't know how many of you have seen the video. In the moment, we have been able to do full scale, and I will stop share, and then I'll share the video for you. Just how many? So I bring the presentation back. So this is not an easy journey. From the beginning of we start with conceptual model about treating tailings to the technology readiness took us about 10 years. And I do acknowledge that persistent industry support from Rio Tinto and KOL been able to enable the translation here. How do I go here? So it is a challenging journey, but it's very rewarding. So translational research, if you want to make it sustainable, you need to be progressively deliver industry impact. In the commercial world, investment needs gradual return. So you can't tell the industry partner to wait for 10 years and come back, see what happens. So it is an integrated multidisciplinary team which continuously involving good ideas built and driven by capable R&D personnel, and then gradually provide the outputs and deliver and translation into operational adoption, more or less. That will enable sustained industry engagement and investment. And as a professional researchers, I suppose this is our mission to drive the automobile going forward and to target and align your research ideas with industry challenges and needs. I think I bring my talk to here a little bit earlier. Then, if any questions, please ask me. Thank you.
Thanks, Longbin. So welcome any questions which people would like to post in the chat. I'd just like to start with one question, perhaps, while people are thinking about their questions. You mentioned this process of scaling up, particularly from what you were calling the sort of proof of concept to what you were calling the feasible technology. You mentioned that you need to take your time, and you also mentioned that you need to really analyze the system and so on. So I'd be quite interested in what you think about why does it take so long, and then perhaps what can be done. What is the best way to go about that? I'm interested in your thoughts to expand on that aspect a little bit.
The reason to take so long sometimes is the journey of understanding. You need to understand where do you go. So, like for example, field trial or semi-field trial, you need multiple seasons to test the response. So you need to observe what happens. Is that within the range of expectation? Then you will start to analyze and devise remedial measures, try to manage that change. If that change is beyond what you want, you need to find the management system or management tool or engineering tool, try to make sure it works. Or you need to bring that learning into your we call constant improvement. This is often happens even in the corporate world. They call ongoing improvement in your business operation. The same with translational research. It's not just doing one experiment and voila, everything comes out. We just put everything in the suitcase and deliver. It's constantly observing, reflecting, refining, improvement, adjustment. Sometimes you need to certain aspect of the proof of concept, you might need to trim it off. You might have to discard it. Sometimes you might have to bring in new aspect, make sure it works. And another thing, just finish off your question is, when the process works really well in one defined context, you really need to start to diversify the operational context to understand your operational tolerance range. Because if you blindly sell your technology to an operational context as the condition doesn't work, you're going to ruin your reputation. Thank you. I can't hear you, Tom.
Yeah, it just took me too long to unmute. There is a question here. I just read it out. Thanks, Longbin. That was fascinating. What are the greatest misunderstandings that researchers have about industry and vice versa when it comes to translational research? Things that would make the collaboration and processes smoother if each knew about the other. Would like to comment on that one?
Yes, actually, this is more related to a talk I gave last week. Is what is the truth of industry engagement? Academics, we are academics, all right? Academics are cats. We have our freedom of thinking and freedom of action, and we do enjoy our discovery of phenomenon and curiosity. Conventionally, government put a lot of investment, so academics have the the enjoyment to look at more the theory side and do not have to think ahead how to bridge into the industry, because government sections often design extension, research stations, etc., to bridge that gap. But for us, but this day and age, unfortunately, industry, society, government expecting academics to go forward, step forward, and to fulfill that role, to extend our academia style of thinking and operation into the business world. So I'm afraid the younger and new generation of researchers not only have to be excellent in research, but also have to have business sense. So another thing to answer that is sometimes the academic promotion system favor the publication-driven model. That's often will make especially young and the early and mid-career researchers to hold back, step into the industry partner research sphere, because that needs a lot of time, and on surface you may not be able to publish so many papers, etc., etc. So to do that, translational research is not single person's job. It's a team. You need the senior leaders to be involved. The senior leaders has to have the passion. The team members have the passion in solving the problem, to structure fundamental discovery and theory. I do publish papers. My members publish papers. We have this ARC discovery projects. We also have ARC linkage projects. But the senior ones, like me, I take a lot of time into the field, try to bring those questions, try to integrate our discovery into the field operation. So you do need a good team to have that collaborative work in order to achieve the translational impact and purposes.
Thank you. So there's no more additional questions in the chat, but I do have one question. Oh, here we go. Here we go. I spoke too soon. So additional comments to the previous question. First, industries is governed to cost and time of operation. For example, a mining company is governed by mine life. If mine life is short, company will not invest greatly in research program. Do you have any sort of thoughts on those comments around the questions of mine life and investment?
That's a very good question, but I think this day and age, I don't think one companies only have one mine to operate. A company have a suite of mine to operate. So when you invest in research, you have a shared benefits. Work done on this site can benefit the other sites. So I think any committed long-term sizable investment should aim for industry sector, not just a mine. Solving mine-specific question or problem with existing knowledge, to me, that's a very good consulting work of improvement. May not warrant sizable long-term commitment from industry to make translational research. Translational research should strategically aim for very significant impacting the large financial basis and environmental risk basis.
Okay.
Otherwise, you can adapt existing knowledge and methodology to solve your site problems.
Sounds good. Thank you. So my final question is, what are your thoughts for where to next? I mean, you've talked about this work and you've talked about the very nature of the academic process and the applied process, but you've also talked about some examples. So where are you thinking next in terms of the work that you're leading and the work that you're driving? Like to tell us a little bit about that?
So you terms in terms of my own work or for the colleagues?
Well, I was asking for you, for your
Okay.
work. Yeah.
To me, my next milestone of the rest of my career is commercialization. I think to make the technology really useful, we have to lead by example. Leading by example, we have to demonstrate, because a lot of new technology often is generation game changing. We cannot expect existing industry players just to plug in and use it. Need a journey, need someone to demonstrate that, to show the sector, then allow the time the sector can assimilate, absorb, and take over that technology. So it is challenging, it's not easy, but I'll do my best to do that. So hopefully we can transit a lot of this technological know-how from the current generation into more of game-changing generation. For example, in the rehabilitation phases, how can we transit from currently very much engineering-focused approach and concept into more nature-based and to leading into sustainable outcome. That's my thoughts.
No, I appreciate it. So it has actually resulted in an additional question, and this is also to you, Longbin, about you specifically. So the question is, what technologies have you been able to develop and patent, and do they apply more broadly to mine site rehabilitation?
The one we really patent is the bauxite residue technoso, bauxite residue treatment technology. We pretty much gave away the iron ore one for the benefits of the community, of course. So we published a lot of things. The bauxite residue is a worldwide problem. It's a very sector focused and specific, much more consistent. We all know the current way operation costs a lot of money. So we hope, I think UniQuest is in the phase of commercializing that. And hopefully in the next 2 to 3 years, we're able to help whichever company interested in it to do the real work in the field.
Okay. Well, look, that's the end of the questions. So maybe we wrap it up there. Thanks also for a very, very interesting presentation and for addressing the questions. And we see you again soon for the next webinar. And please join me in thanking Longbin. Thank you very much.
Thank you. Thanks for the opportunity. Thanks, everyone. And talk to you later. Thanks. Bye.